Some discoveries feel small at first glance. A dip in a star's brightness, a faint spectral imprint, a whisper of gas crossing a detector billions of kilometers away. But every so often, the universe delivers something that refuses to stay small. A signal that interrupts expectations. A dataset that makes entire research teams pause, not because it is loud, but because it is too precise to ignore. About 40 light-years from Earth, orbiting a dim red dwarf star known as TRAPPIST-1, lies a system that has become one of the most intensely studied regions in modern astronomy. Among its 7 rocky planets, one world, TRAPPIST-1e, has emerged as a leading candidate for habitability. Not because it looks like Earth at first glance, but because it keeps surviving every attempt to rule it out. When the James Webb Space Telescope turned its attention toward this system, expectations were cautious. TRAPPIST-1 is a small, cool dwarf star, barely glowing compared to our Sun, but notoriously volatile in its early life. Scientists expected radiation damage, atmospheric loss, and likely barren worlds. Instead, what began to emerge from the data was something far more complicated: ambiguity that refused to collapse into a simple answer. TRAPPIST-1e sits in the so-called habitable zone, where temperatures could allow liquid water under the right conditions. But habitability is not just about distance. It is about atmosphere, chemistry, and stability over billions of years. And that is where the real mystery begins. Early models assumed that any Earth-sized planet so close to a red dwarf would lose its atmosphere quickly. Stellar flares, especially in a star's youth, can strip away light gases and leave behind a barren rock. That expectation shaped much of the initial skepticism. Yet TRAPPIST-1e did not fit cleanly into that outcome. Using transit spectroscopy, JWST analyzed starlight filtering through the planet's atmosphere as it passed in front of its star. The goal was simple: detect chemical fingerprints that reveal what the air is made of. Hydrogen-rich envelopes were quickly ruled out. So were thick carbon dioxide atmospheres like Venus, and thin Mars-like remnants. What remained was uncertainty, but of a very specific kind. The spectral data did not show absence. It showed structure without clarity. A pattern consistent with a secondary atmosphere, possibly dominated by nitrogen, with traces of gases like water vapor or methane in quantities too subtle to confirm definitively. This is important, because a nitrogen-rich atmosphere at around 1 bar pressure would resemble Earth's own atmospheric balance far more than any other known planetary environment. If that interpretation is correct, then TRAPPIST-1e could support weather systems, heat circulation, and even stable liquid water under the right surface conditions. But there is a complication that cannot be ignored. TRAPPIST-1 is a tidally locked system. One side of the planet may permanently face the star in daylight, while the other remains in endless night. That creates extreme temperature gradients that could, in theory, destabilize an atmosphere. Yet climate simulations suggest something surprising: with sufficient atmospheric density, heat redistribution is possible. Winds could continuously transfer energy from the day side to the night side, smoothing temperature differences. In such a scenario, the most stable environment might not be the day side or night side at all, but a thin transition region between them, the terminator zone, where twilight conditions could persist indefinitely. In that narrow band, liquid water could exist under stable pressure and temperature ranges, creating a ring-shaped habitable region around the planet. Life, if it exists, might not spread across a globe but instead cling to a perpetual dusk. Still, even this possibility depends on a fragile condition: atmospheric survival. Red dwarfs like TRAPPIST-1 are not gentle stars. In their early stages, they can unleash intense flares and radiation bursts capable of stripping planetary atmospheres. A storm that would be extreme on Earth could occur frequently in such systems. Over time, however, TRAPPIST-1 has matured and become more stable, entering a quieter phase of its lifespan. This introduces a paradox. The same star that could destroy a planet's atmosphere early in its history might later provide the long-term stability needed for life to develop. If TRAPPIST-1e managed to retain or regenerate its atmosphere after that violent period, it would represent an extraordinary case of planetary resilience. And resilience, in astrobiology, matters as much as chemistry. Another factor strengthens the case for potential habitability: tidal heating. TRAPPIST-1e does not exist in isolation. It is part of a tightly packed system of 7 planets, each gravitationally interacting with the others. These interactions can stretch and compress the planet's interior, generating internal heat. On Earth, most internal heat comes from radioactive decay. On TRAPPIST-1e, tidal forces could contribute significantly more energy. This heat could drive volcanic activity, maintain a molten core, and potentially support a magnetic field. A magnetic field is crucial. It acts as a shield against stellar radiation, protecting the atmosphere from being slowly eroded by charged particles. Without it, even a thick atmosphere can be stripped away over time. If TRAPPIST-1e has both tidal heating and a magnetic field, then its chances of long-term atmospheric stability increase dramatically. This combination, atmosphere, heat redistribution, and magnetic shielding, is rare. And that rarity is exactly why the planet has become so important. Yet JWST has not delivered certainty. Instead, it has delivered something more scientifically unsettling: a system that refuses to collapse into a clear classification. Not clearly dead. Not clearly alive. Something in between. Future observations are already scheduled. Multiple additional transits will refine spectral resolution, reduce noise, and attempt to isolate molecular signatures with higher confidence. Scientists are particularly focused on detecting consistent traces of water vapor, carbon dioxide balance, and methane fluctuations. Even a small detection of water vapor, if confirmed repeatedly, would dramatically strengthen the case for habitability. But even then, life is not guaranteed. A planet can be habitable without being inhabited. It can have all the right conditions and still remain silent. That possibility is what makes TRAPPIST-1e both scientifically exciting and philosophically uncomfortable. Because what JWST is ultimately doing is not just measuring a planet. It is narrowing uncertainty about whether Earth is unique, or simply one example among many that managed to survive long enough for chemistry to become biology. There is also another layer to this discovery that is often overlooked: time. TRAPPIST-1 is far older than the Sun's stable future, potentially offering a timescale of trillions of years of stellar lifespan. That means if life can emerge there, it could persist for periods far beyond Earth's biological horizon. Entire evolutionary histories could unfold in environments that remain stable long after our own planet becomes uninhabitable. In that sense, TRAPPIST-1e is not just a candidate for life. It is a test of durability, of whether life is a brief accident tied to specific conditions, or a recurring outcome in stable environments across the galaxy. For now, the answer remains open. The data is precise, but incomplete. The signals are suggestive, but not definitive. The planet is close enough for detailed study, yet distant enough that every conclusion requires caution. And that is what makes this moment so significant. We are no longer guessing based on distant starlight alone. We are analyzing the atmosphere of an Earth-sized world, in a system not far in cosmic terms, asking a question that has followed humanity since the first moment we looked up. Is Earth rare, or simply the first example we happened to study closely? TRAPPIST-1e has not answered that question yet. But it has ensured we cannot ignore it anymore.